So one of the shifts that you'll notice from chapter 2 to chapter 1, hopefully, is that in chapter 2 we're starting to look at individuals in a set of data, right, and where they stand, as opposed to here's the center and shape and spread of all of the data. So like in chapter 1, I would look at this stem and leaf plot here and say, it looks like the shape of the distribution is sort of skewed to the left a little bit, right? If I took this and stood it up, I have one number down here. Most of the data is up here in the 80s and the 90s, and then it starts to tail off a little bit, maybe slightly skewed to the left. And I talk about, what a typical number of wins is for a major league team. Now we shift here, and question A says, what is the percentile for each of these teams? So I want to dive in here and look at this 66 games, right? Where does that sit? That's right here in the box plot. That's the Minnesota Twins. They won 66 games. So as a percentile, what I do is I look and see that there are 3 observations that are below that. That's sort of the convention your textbook uses. Sometimes you'll hear someone say it's your percentile is the percentage of observations at or below that observation. So if it was the percentage of observations at or below it, it would be 4 out of 30, right? There's 30 total. But we would just say that would be 3 out of 30, okay? Which would be 0.1, or the 10th percentile, right? 3 out of 30 equals 10th percentile, okay? What that means is that 10% of teams had fewer wins than the Minnesota Twins. Washington Nationals, they won the most games, right? So you would say they're the 100th percentile, or we're just going to go with 29 teams that are below them out of 30. So we would have 29 divided by 30, and we want to turn that into a decimal or a percent. So as a decimal, it's 0.96 repeating, or 0.97. So I would just round that and say that they are the 97th percentile. Okay, and then finally we have the Texas Rangers and Baltimore Orioles. Both of them won 93 games. So you can see those 2 observations here, a 93 and a 93. I guess the quickest way would just be to count up the other way. We know this is going to be out of 30. So it might be quicker for me to count the number that are at or above them and then subtract. So I have 1, 2, 3, 4, 5, 6, 7, 8. So that means I'd have 22 that are below them. So 22 divided by 30. And again, convert that to a percentage, and I get 73, or 73rd percentile. So that's one way that you can always measure a person's relative standing. It's their percentile, right? So if you are, if your GPA is at the 98th percentile, that's very, very good. That means that 98% of everyone's GPA is below yours, right? If somebody's height is at the 10th percentile, that they're going to be below average height. You see, 90% of people you would encounter would be taller than them, right? So the next graph we're going to look at, you probably have seen at the doctor's office, especially as you're growing up. As a child, you go to the pediatrician and they'll show your parents your like a height and weight chart, and they show you what percentile you're at a lot of times. So this is called a cumulative frequency graph, or an OGIV. Okay, so what we have, we're going to look at medium incomes, right? So one group that, and this could be looked at as like a histogram, like what we did in the last chapter. So there was one observation that was between $35,000 and $40,000, right? Then there were 10 that were between 40 and 45, and we can almost sort of see that how this histogram would build up, right? It's going to be the median income is probably going to be close to somewhere in the 45 to 50,000, right? Because this is your highest frequency here. You have 14 in this group, and then 12 in this group, and so on. So median might live in either one of these groups. And remember what the median would be. It would be the 50th percentile. So we can actually come over here and see what's happening over in this cumulative column is we're adding them up. So we had 1 person in this group, 10 in this, which means we had 11 at or below. So now we're starting, this cumulative is giving us the number that are at or below this income. They keep on adding them. So by the end, we get to 100%, or all 51 observations. There's 50 states and the District of Columbia included in this, okay? So we can see our median number would have to live in this bracket, right? Because right here we're at the 49th percentile, and the median is the 50th percentile. So somewhere between 50 to 55,000. So now let's look at what that looks like graphically. This is an ogive, right? So we said in this window here, 50 to 55,000 is where we might guess the median to be. I can't draw a real great straight line, but if I come across, this is my cumulative percentile. So the 50th percentile will be right here, and then we can drop down from that point. We can see 50,000 is about that median value. If I wanted the 80th percentile for income, pretty shaky hand here, but I would come over to where the graph intersects and I'd come down and see that's going to be about 60%. I can get a much more accurate view looking at the table, or if I had some kind of straight edge or ruler to make those connections. But that's how we look at that ogive. And like I said, a lot of times I'll ask students if they've ever seen a graph like that, and sometimes they remember, going to the pediatrician's office growing up is something that where that would be familiar, and they can relate to that. So down here, use the cumulative frequency graph for the state income data to answer each question. At what percentile is California with a median household income of $57,445? So $57,445, I'm going to say that's going to live right here. I'm going to do my best to come straight up to the graph and then straight over. So if you estimated that as about the 80th percentile, right? And I can see from your work here how you drew those lines in and would arrive at that. That would be a pretty good estimate. Estimate and interpret the first quartile of this distribution. So what's the first quartile? We go the other way now. Quartile means the first quartile will be the 25th percentile. So here's 0.2. This would be 0.3. I don't want to go 0.3. I want to go in between 0.2 and 0.3, 0.25. Try to draw a straight line here. I'm going to estimate about 45,000. Okay, and so hopefully you can see how we can go in either direction. I can take an income value and see what percentile it is, or I can look for a particular percentile and see what its value is. Okay, so we've got percentiles, and now we have z-scores. So to understand a z-score, you have to understand the concept of standard deviation and how it relates to the mean, right? Standard deviation of a set of numbers is, on average, how far each individual number falls from the mean. So to measure relative to the mean. So a z-score measures specifically how many standard deviations somebody is above or below the mean. So if you asked me about your chapter 1 test, for example, and I didn't tell you, and you said, how did I do? What did I get? And I said, I'm not going to tell you your raw score, but your z-score was 1.5. You should feel pretty good about that, because whatever the mean is, you're 1.5 standard deviations above it. So you'd have to know the mean and the standard deviation to figure out what your raw score was. But you know that your relative standing to the rest of the class is above average. Okay, and depending on what the distribution looks like, 1.5 standard deviations could be pretty high above average. Okay, and we'll talk more about what that means specifically with a normal distribution. But right now we're just saying, just straight away, the z-scores, how many standard deviations you are above the mean. So a positive z-score means that you are above the mean. A negative z-score, if you came to me and said, how did I do my test? And I said, well, you got a negative 0.3 z-score. Well, that means that you're 0.3 of a standard deviation below the mean. So you might not be real happy about that. You'd feel like, well, compared to everybody else, I scored below the mean. Not really far below the mean, but below it. If you had a z-score of 0, that means that your raw score was equal to the mean. We'll come back and think about that in a little bit in one of the last questions. So here we have the average number of wins for a baseball team is 81 with a standard deviation of 11.9. So how did the New York Yankees compare to everyone? We would use their z-score. Well, they won 95 games, which is above average. So I take 95 minus 81. That's the first piece of this. And I can see, well, they were 14 games above the average. But depending on what the standard deviation is, that may or may not be a lot above or below the average. So I take that 14 and divide by 11.9, which was the standard deviation, and now I can give it even a little bit more meaning here and say that they were 1.176. I'll just round to 2 decimal places. They were 1.18 standard deviations above the mean. Okay, and remember, it says find and interpret, right? So this means that they were 1.18 standard deviations above the average. That's what that means. Okay, so now the Mets, other New York team, not as great. So they only won 74 games. So I'm going to take 74 minus 81. So I'm going to get a negative number now, and I'm going to do the same thing, divide by 11.9. So what happens here, 74 minus 81 is negative 7. And then I'm going to divide that by 11.9. And I get negative 0.59. So my interpretation would be they are about 0.6 or 0.59 standard deviations below the mean in wins. Okay. So we can stay with baseball here, and we have 4 very famous players here, power hitters that hit a lot of home runs over their career. But some of them hit home runs in an era when a lot of people were hitting home runs, okay? So what we want to do is compare, how do they compare to the average number of home runs, at their particular time? Like you see, Babe Ruth hit less home runs than everybody else, but the average number of home runs when he was playing was only 7.2, right? Whereas you can see with when Mark McGwire and Barry Bonds played, the average number of home runs is much higher. So we're going to go ahead and compute all of their Z-scores. Okay, so for each person, you're going to take their raw score. So for Babe Ruth, for example, you're going to take 60 minus 7.2, and then you're going to divide by 9.7. That's his Z-score. So the guy who has the highest Z-score is going to have the best performance relative to his era. Okay, so assuming I did my Z-score calculations correctly here, we can look at these particular Z-scores. All of these guys hit a lot of home runs, but we should be able to look at this and see relative to their peers who performed the greatest. So I'll let you answer that one in our Edpuzzle question here. So hopefully you looked at the data here and decided that compared to their peers, it looks like Babe Ruth probably was the best, has the highest Z-score. So, relative to their peers, we would say he was the best home run hitter compared to them using the Z-scores. So the next thing I want to look at with you is what we would call linear transformation. And I want to think about the effects of that. So here you have a group of test scores. There's 30 test scores. You see 30 dots here. Looks like the highest possible score is a 50. So we could talk about the center, shape, and spread, but we have all of the statistics here. We have a median of 37. They give us a mean of 35.8. So we can see it does look like it's a little bit skewed to the left, or maybe these outliers over here are making the mean a little bit smaller than the median, right? When the mean is smaller than the median, we know from the last chapter that usually means that the data is skewed to the left, or there's some low outliers. So teacher's going to be really nice and add 5 points to everybody's score, right? So what happens when we do that? We can look at the graph. Well, everybody's score just got pushed up 5 points. They all moved to the right. So we can see the center definitely moved, right? It went from a median of 37 to a median of 42, 35.8. We just add 5 to it. So we can see to find the new measures of center or any relative standing, they all went up by 5, right? 12. The minimum went from 12 to 17. The max went from 48 to 53. Shouldn't be a big surprise. But what I want you to take note of, though, is that our measures of spread, when we added 5 to everybody's score, none of the measures of spread changed at all. And hopefully that makes sense to you. If I add 5 to everybody's score, I haven't changed the spread at all, right? Like the max of 48 went up 5, but so did the minimum. It also went up 5. So none of my measures of spread change when I add or subtract a constant to a set of numbers, right? That's the first part of a linear transformation. If I add a constant to everything, then the measures of center will change, but the measures of spread will not change, okay? Now let's look at what the teacher does next. The teacher says, it's going to be easier for these students to understand how they did if I measure it out of 100. So if it was out of 50, all we have to do is multiply everybody's score by 2. So if you had 40 out of 50, then we just multiply the 40 by 2, and it's going to be 80 out of 100. So now look what happens when we multiply everybody's score by a constant. Notice what happens. Here's your standard deviation. It also doubled. Measures of spread changed, right? Because think about it, if the minimum, I'll just make up a couple numbers. If the minimum is 30 and the max is 50, that's a range of 20. Well, if I double both of those, now I'm talking about 60 and 100, and that's a range of 40. So you'll notice your IQR has now doubled, okay? And the range has also doubled. And not a big surprise, our measures of center, they've doubled too. So when we talk about measures of spread, if we add a constant to everything, the measures of spread won't change, but the measures of center will. But if we multiply or divide by a constant, and think about, that's what a linear transformation is, right? If you have a linear equation, y equals a plus bx, okay, this is your y-intercept, is your constant. We add or subtract some constant, and then we have our slope or our multiplier. This multiplier will change both. It'll change center and spread. This thing here is only going to change measures of center. Okay, so let's try an example where we flesh that out. Okay, so we have the data on taxi cab rides, and what they give us is the fare. The fare equals $2.50 plus $2 times every mile. Okay, but now they give us the average fare, which is $15.45, and they give us the standard deviation. But what they would like is the mean and standard deviation of the lengths of his cab rides. So let's start with this equation here. The equation for fare is 2.5 plus 2 times length or miles. Right? Well, that's what this question is asking us for, is miles. So the first thing I have to do is back transform this equation to solve for miles. Pretty easy basic algebra here. Subtract 2.5 from both sides. So I would have, and then I would divide both sides by 2. So I would take the fare, subtract $2.50 from it, okay? And then we divide that all by 2. It's a two-step deal. And that's going to give us our miles. So what we want is the mean and the standard deviation, okay? So remember what happens here for the mean, both of these will affect the mean. When I subtract 2.5 and I divide by 2, that will transform the mean. So the mean in miles, I'm going to take the 1545, which is a fare. I'm going to subtract 2.5 from it, and I'm going to divide that by 2. And I get 6.475. Is an average length. Okay, so I back transformed. If the average fare is $15.45, that means the average length of a ride is 6.475, right? 6.475 multiplied by 2, add 250, gets me that average fare. Now I want the standard deviation of the fare. Sorry, not standard deviation of the fare, but standard deviation of the length. Okay, so standard deviation measures spread. Well, this transformation, this minus 2.5, is not going to affect spread. Remember, if we subtract the same number from anything, it doesn't change spread. So I'm going to take my $10.20, which is the standard deviation in fare, and all I got to do is divide that by 2 to get back to the standard deviation length. So I think that's going to be 5.1 miles is the standard deviation length. Okay, so linear transformation, it's kind of a tricky little application of it, because you had to do some algebra first. You had to see, like, well, if I want to get, if this is for fare based on miles, I got to rewire it and go backwards. And then you apply the concepts that we're talking about here. Both will change measures of center. Only multiplying or dividing will change a measure of spread.